Hello, this is demo for our project file compression and regeneration. Our group member is Xinyi, Klaus, Ellie, and me, Lydia, Zhao. So firstly, I will give a brief introduction of our project. In our project, we compare the performance of 4 lossless file compression and regeneration algorithms, namely run-length encoding, Huffman encoding, and LZ77 and LZW. We will evaluate their performance under different circumstances, including limited RAM and compatibility with different operating systems, using metrics such as compression ratio, compression time, and decompression time. Our main goal is to understand the strengths and limitations of each algorithm and provide recommendations for their usage in different scenarios. And next is the motivation of our project. So nowadays, the efficient lossless compression algorithm is needed for all kinds of mainstream data types. But previous studies mainly focus on specific data types with unlimited RAMs on unspecified systems. But the available RAM and operating systems can significantly impact the performance of compression algorithms. Our state-of-art lossless compression algorithms will be studied and compared on multiple systems with different RAM capacities. Our goal is to develop recommendations for practitioners and the researchers to choose the best compression algorithm for their specific usage. The thorough testing strategies will be used, including a wide range of input data sets and specific metrics for objective and measurable comparisons. And next is the problem description. So firstly, there are numerous compression algorithms. Various lossless compression algorithms exist. Each of them has its strengths and weakness. There might have difficulty in determining the best algorithm for a specific use case. And secondly, there are device limitations. So varying RAM capacities across devices from smartphones to computers. The performance of compression algorithm may be affected by the available RAM. Last is that the operating system compatibility. So different compression algorithms on various operating systems may have different performance, and there are needs for efficient data management across platforms. So our project is doing the comprehensive comparison and evaluation. And next, Ellie will introduce the algorithms we used in our project.
Thank you, Lydia. Now let me quickly go through the algorithms. So the first one is run-length encoding. It is a compression technique that is particularly useful when dealing with data that has consecutive sequence of identical symbols, such as characters or pixels. So the idea behind RLE is that we can replace this consecutive sequence with just a single symbol and count how many times this symbol appears. This makes RLE an efficient method for data with long runs of the same symbol. For the data structure, RLE uses a list as the output buffer to store the compressed sequence. Next, Huffman coding. The idea behind Huffman coding is to assign variable length binary codes to characters based on their frequency. More frequent characters are assigned with shorter binary codes, while less frequent characters receive longer codes. To create the optimal code assignment, a binary tree called the Huffman tree is constructed, and the least frequent characters are at the bottom, and the most frequent characters are closer to the root. In this way, we can achieve less searching time. LC77 is based on dictionary encoding, sliding window, and string matching. It works by replacing repeated data with references to prior occurrence or matches, using a sliding window to track process data and a look-ahead buffer for matching. The algorithm outputs references when match is found, new data when matches are not found, and adjusts the sliding window accordingly. LZW is a dictionary-based compression method that encodes data by substituting repeating patterns or sequences with shorter codes. The encoding process creates a dictionary of repeating patterns to replace them with shorter codes. And the decoding process reconstructs the original data using the dictionary to translate the shorter codes back into their original patterns. Simulation setup. We mainly use 3 well-known datasets to test and compare the algorithms, including the Calgary corpus, Canterbury corpus, and the large corpus. The corpus includes files such as novels, scientific articles, computer programs, and large text files, which can be challenging to compression algorithms. These files are representative of different types of data and sizes, like sizes ranging from 8 kilobytes to 4 megabytes, making them a good benchmark for evaluating compression algorithms on real-world data. So to evaluate compression algorithm, the performance of compression algorithm across various operating systems, we have set up the testing environment in IDEs on Windows 11, Mac OS, iOS, Android, and Linux. The table shows the system version, the memory and the processor of the hardware that the operating system is installed on. And please note that for Android, we installed an Android emulator on Windows, and for Linux, we installed a virtual machine Ubuntu on Mac. The algorithms will be interpreted by Python 3 to ensure cross-platform compatibility and consistent results. RAM limitation. To set up the RAM limitation for the simulation, we used a Python library called psutil to set the maximum amount of memory for the current thread. The psutil library is supported in IDEs on all platforms we compared. The simulated limited RAM usage is set as 256 megabytes, 512 megabytes, 1 gigabyte, and 2 gigabytes. During the simulation, 3 metrics are measured, including compression ratio, compression time, and decompression time. Next, we will have Xinyi to present the results.
Thank you, Ellie. With our simulation plan, we performed our tests on different platforms with different RAM capacities. So here we have a brief summary of the results. Basically, RLE has a wide compression ratio range and fast performance, but has poor compression for daily use text data. Huffman offers a stable compression ratio and fast processing times, being consistent across platforms and limited RAM scenarios. LZ77 has a varying compression and ratio and inconsistent performance with longer compression process. LZW has a stable compression ratio, reliable speed performance, and it's not very heavily influenced by the available memory. So over here, this is the raw data table for each the algorithm's performance on Mac, Linux, Windows, iOS, and Android with different RAM capacities. This as well. So basically, those are raw tables. I think it's kind of hard for us to actually see the raw table data. So here we have the 2 graphs giving us a good idea of the average compression ratio and overall processing times. We can see that LZW demonstrates the best average compression ratio, while RLE demonstrates the fastest overall average processing time, followed closely by the LZW with a slightly slower time. On this slide, we can take a look at some of the other graphs. So basically, this graph shows the compression ratio versus compression time for the 4 algorithms. The top graph represents Windows, Mac, and Linux platforms, while the bottom graph represents iOS and Android platforms. We can see that there is a similar pattern in the PC operating systems and slight variant pattern on the phone operating system. Generally speaking, if we prioritize the compression ratio, then LZW is recommended, and RLE is better for faster compression time. So if we prioritize compression times, then RLE might be a better choice. We also find that LZW and Huffman both provide a balance between compression ratio and time. Also, for mobile operating systems, LZ77 is generally slower on Android, so it's less suitable for that platform. Next, let's take a look at the performance graph. So this graph shows the performance of the Pro algorithms, again, on those systems over different capacities, RAM capacities. On the left, we have the compression time comparison, and on the right, we have the decompression time comparison. We can see that LZW and RLE constantly perform well for compression time across different RAM capacities. We can also notice that Huffman has a longer decompression time, and thus it might not be ideal for use that require fast decompression, like real-time video compressions. On the contrast, we can also see that LZ77 has a much better decompression performance than its compression performance. As you might notice before, LZ77 has a really long performance, really long time for compression, and also in this graph, we can also see that. So LZ77 actually works really nice for decompression. Generally speaking, again, LZ77, RLE, and LZW might be good choices for heavy decompression tasks, such as unzipping large files or handling high redundancy image files. Then on the next slide, there's another graph showcasing the algorithm's performance on Android and iOS under different RAM capacities. Here we can see that RLE is a dependable choice for both platforms, providing balanced compression and decompression time. LZW excels in decompression on Android, but not on iOS, making it more suitable for Android users. Huffman's decompression time here remains longer on both platforms, while LZ77 continues to excel in decompression. However, finally, we have to say that it is essential for users to consider the platform and use case when selecting an algorithm, as performance may vary depending on the task and platform. Next, we will have Klaus talk about the conclusion, trade-off, and all that.
Okay, thank you, Xinyi. So we talk about all the methodologies we have and discuss about the results, and I will do the summary based on the trade-offs, conclusions, and the limitations. So the first thing is the trade-offs. So generally, people may think about the compression algorithm as a better one if they can compress it into a smaller size file after the algorithm's processing. But it turned out to be a very higher compression ratio is often resulted in a much more complex algorithm with a very difficult implementation. So for example, Huffman requires about 400 lines of code, whereas LZ77 only needs about 50. So sometimes maybe the high compression ratio is not really necessary, and it pushes people to choose the right algorithm instead of pursue the very high compression ratio. And another thing is generally algorithms has very high time complexity. They do not require much extra space. For example, LZ77 is based on string matching and only 2 string is okay, but Huffman is based on recursive tree and it requires a very large tree space. And another thing is very different type of data. They require different approaches. So for example, LZ77 RLE, they are based on string matching process and they can do better for the task that has very similar characters. But for those who has random characters, they might not be the best choice. Like Xinyi has discussed before, LZW and Huffman, they are better. And that makes us to reach the conclusion for our presentation. The first conclusion is RLE, LZ77, they all outperform for those strings with similar characters, repetitive patterns. And also Huffman and LZW, they show very consistent pattern across all kinds of files. And moreover, the optimal algorithm depends on a lot of factors. So for example, the file type, the platform memory, and the balance between compression ratio and processing time. So if a person wants to make a decision about which kind of algorithm to choose, they must think about these factors before really selecting an algorithm. And another thing is Android devices is generally slower in comparison with all other kind of platforms in case of compression speed. But for the compression ratio, they're roughly the same. And that brings us to the limitations. So in retrospective, we're looking back into our approaches generally for our research. So one thing is we only tested 4 algorithms. All of them, they are lossless. And there are also other kind of lossless algorithms available on the market. And there are also lossy algorithms, but we only choose the 4. That's the most classic one for our research. And also we specifically focus on the test instead of focusing on audio, video, and we use the test, we use some kind of file test to mimic the image. And in our future research, we are also focusing on the audio and video part. And one last one is all the simulations we perform, they are carry out on certain platforms, including like a virtual machine. So they might not be one of the best ways to do the simulation, because it's, after all, it's very different from a real life, especially the Android. We use PyDroid instead of running it on an Android phone. So that's pretty much about the conclusion part. Thank you so much for listening.